Welcome to the session on integration by parts. The objectives for this session are to integrate functions by using integration by parts. Recall the product rule for differentiation, namely d dx of uv equals u dv dx plus v du dx, where u and v are functions of x. Rearranging the product rule gives this expression: u dv dx equals d dx of uv minus v du dx. If we now integrate both sides of this equation with respect to x, we have integral u dv dx dx equals integral d dx of uv dx minus integral v du dx dx. And this equation is equivalent to integral u dv dx dx, which doesn't of course change, equals uv, since this is the integral of d dx of uv dx, minus integral v du dx dx, which doesn't change either. This method is called integration by parts. We're going to save this formula for reference here, and then use it to help us to integrate more complex functions. We're going to write the function we want to integrate as u dv dx, and then choose what to set as u and dv dx. So let's take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. We are required to integrate x sin x with respect to x. So remember that we want to decide what to set as u and what to set as dv dx. Now, in this integral, you can see that we can easily differentiate sin x on its own. However, it has the x attached to it. So a clue in this is that if we let u equal x and dv dx equals sin x, then the x variable can be got rid of, so to speak, when we differentiate u, and this is part of the formula for integration by parts. So let's take a look at what we're trying to do. We let u equal x, as we said earlier, and dv dx equals sin x. Notice that in our formula we need u, we need dv dx, we need v, and we need du dx. So let's differentiate and integrate respectively the two functions. So differentiating u equals x with respect to x, we have du dx equals 1. And integrating dv dx with respect to x gives us v equals minus cos x, since of course we're integrating sin x. Now let's apply the integration by parts formula. So let's plug in the various values. So we have u equals x here, v equals minus cos x here, minus the integral of v, which is minus cos x, times du dx, which is equal to 1. And we're integrating this expression with respect to x. So let's tidy up. We have that our integral is equal to minus x cos x plus integral cos x dx. And so we have that our integral is equal to minus x cos x plus the integral of cos x, which is sin x. Notice that the x that we were looking at right at the start within our original integral has now disappeared because we set that equal to u and then differentiated. So we had du dx, and so this x fell away when we were considering it in the light of the formula. And of course, so we have our integral, and we need to add the constant of integration c at the end, as we can see towards the bottom of the screen. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. We are required to integrate I equals integral x cubed ln of x dx. Consider this integral for a moment. Can we set u equals x cubed and dv dx equals ln x, or vice versa? If we consider these for a moment, then we need to think about whether we can integrate or differentiate ln of x. Since we can easily differentiate ln of x, we need to set this as u, because we can't integrate ln of x easily. And therefore we need to set dv dx as x cubed, as shown here. So this implies that du dx equals 1 over x, since we can differentiate ln x, and v equals x to the power 4 divided by 4, which is the integral of x cubed. Now we can apply our formula, integration by parts. On the left-hand side we have I, which is equal to the integral x cubed ln x dx, or u dv dx in terms of our formula. And on the right-hand side we have uv, which in our example is ln x times x to the power 4 divided by 4, minus the integral of v du dx, which is x to the power 4 over 4 times 1 over x dx. So tidying up, we have x to the power 4 over 4 ln x minus a quarter integral x cubed dx. Gives us x to the power 4 over 4 ln x, as we can see here, minus a quarter x to the power 4 over 4, plus the constant of integration. And finally, tidying up some more gives us I equals x to the power 4 over 4 ln x minus x to the power 4 over 16, plus our constant of integration c. Let's now take a look at another example. Pause the video and have a go. Press play when you're ready to view the solution. Now in this example, you will need to apply integration by parts twice. So let's solve this. We are required to integrate I equals integral x squared e to the x dx. We're going to let u equal x squared and dv dx equal e to the x, since differentiating x squared is going to get rid of these x's, and integrating or differentiating e to the x isn't going to change it at all. So usually when we integrate, we make functions more complex. So in this situation, since e to the power x doesn't change, it's better to leave it as dv dx. So differentiating u equals x squared gives us du dx equals 2x, and integrating dv dx, as we said earlier, is v equals e to the power x. Now we can plug these into our integration by parts formula to give us uv, which is x squared e to the x, minus the integral e to the power x 2x dx, which is v du dx. And so we have I equals x squared e to the x minus 2 integral x e to the x dx. So now we have another integral which we need to integrate. And of course the x before the e to the power x is the troublesome variable. So we need to apply integration by parts again to this integral. So let's do that. We're going to let u equal x and dv dx equal e to the x. So this implies du dx equals 1, and integrating dv dx equals e to the x gives us v equals e to the x. We can now plug this into our integration by parts formula, namely this bit here in particular. So we have u equals x and dv dx equals e to the x, so that's our integral, x e to the x, and uv in our example here is x e to the x, and again referring to our integration by parts formula, v du dx is 1 times e to the x, which is of course e to the x. So the last bit we integrate e to the x dx, as we can see here. So now our integral equals x squared e to the x minus 2x e to the x plus 2 e to the x plus our constant of integration c. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solution. So in this example, we're required to evaluate I equals integral ln x dx between the limits 4 and 1. We're going to let u equal ln x and dv dx equal 1. This implies du dx equals 1 over x and v equals x. Applying the integration by parts formula gives us I equals x ln x between the limits 4 and 1, as shown here, minus the integral between 4 and 1 of x times 1 over x. And we're integrating this with respect to x. So tidying up some more gives us that our integral equals 4 ln 4, plugging in the limit 4, minus 1 ln 1, plugging in the limit 1, minus the integral of 1 dx between the limits 4 and 1. Of course, ln 1 is simply 0, and 4 ln 4 is 4 ln 2 squared, which is 8 ln 2. And now let's integrate. We now have that I equals 8 ln 2 minus x between the limits 4 and 1. And of course, x between the limits 4 and 1 is simply 4 minus 1. So we have that I equals 8 ln 2 minus 4 minus 1. which is equal to 8 ln 2 minus 3, which is the value of our integral. This brings us to the end of this session. If you have understood its contents, you should be able to integrate functions using integration by parts. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.